Guys, I'm excited about this section. I think you should be too. We are at the end of chapter 5. What a wonderful journey it's been, hasn't it been? Where we're done kind of talking about, we're done talking about like the properties of logarithms and exponential functions. And now what we want to know is where we ever going to use this, right? So all of the types of functions that have been really, really useful for not just mathematicians, but scientists and business and branches outside of mathematics has been using exponential functions. So you've probably heard, and I think I've said this before in my videos, like, oh, that grew exponentially. And are you sure about that? Do you know that it was exponential? So what we're going to see is, yeah, there actually are things that grow or decay exponentially. So we're going to look at some applications of the exponential function that are really quite interesting. Maybe you've seen some of these before, but that's all right. They're a good time. So the first thing we're going to look at is our functions or exponential models that have growth, that are increasing. So in this case, what I'm going to look at is population growth. And the funny thing is, well, I don't know if it's funny. But this is really just growth of any kind. So that we are going to label this population growth, and we're going to talk about populations like people, or you can look at fruit flies or bacteria, right? They're all going to grow exponentially. But we also are going to look at money. If I put money into an account that's compounded continuously, then that actually grows exponentially as well. So population growth, the function that we're going to use for this, so my population is a function of time, right? As time goes on, populations increase. So P of t is going to be P naught, or P sub 0. That's going to be my initial population to the kt, where k must be greater than 0 for this to be growth, okay? So again, it doesn't have to be people. It can be, like I said, money. We can talk about how the number of cell phones people own grows exponentially. Anything, and how do we know if it grows exponentially? Well, we take data, right? And we look at data points and we see if we can fit it with an exponential curve. We have Excel programs, we have TI-84s that can actually fit that data, the line of best fit. And if you decide to ever go and take calculus someday, you'll see why that actually works. Those linear regressions, you're minimizing a distance. Anyway, we're here, P sub naught, or P naught, excuse me, or P sub 0. You may have heard of P naught. That's usually what we say for like the beginning. This is the initial population. Now we're not talking about, when I say initial population, I'm talking about whenever we're starting our time. Okay, so clearly T is time, right? So, I mean, if I asked you like, what was the initial population of humans, you'd be like, well, it was 0. So I'm not going to start off at 0. We're going to look at like an example with the population of Wyoming, and I'm going to start with the year 2000. So that's kind of my initial population at time 0, whatever we define time 0 to be, okay? And then K is what we call the exponential growth rate. Okay, exponential growth rate. Again, this is a rate. And so we need to make sure that this is a decimal. So if they maybe give us, it depends on what they give us, but maybe they give us a percentage for the rate, like it grows at 4% or whatever, we want to make sure that that is a decimal. Okay, so this is it. Isn't this exciting? This is my population growth function. So look at this function. We know what this looks like, right? This e to the kt, we know what e looks like. You know, what do we have here? This is time, this is P. And so this is what people mean when they say things grow exponentially, right? What are these numbers in front going to do? So remember, this guy, this P naught in front is going to do a vertical stretch, and this K over here, depending on, if it's less than 1, it's going to be greater than 0. That's going to do a horizontal stretch. But let's go ahead and look at an example. And I'd like to just kind of start off with one that isn't super easy. Like you can, I mean, if someone gives you the K, that's a super easy problem to find, right? So let's look at one maybe that isn't quite so obvious. So let me get a different layer here and do really well here. So for example, the population of Wyoming, now I looked this up. I mean, it was on the internet, so it must be right. I actually think it was from like the Bureau of Statistics, Labor Statistics or something, whatever, of Wyoming. Was 494,300 in 2000 and was 564,460 in 2010. So I want us to do a couple of things. Well, let's assuming does, but it's okay. The population grows exponentially. It's not going to grow super fast. Determine the following. All right, part A. So the exponential growth rate. Let's determine that, which we're going to need no matter what. B, the estimated population of Wyoming. I'll just let you put that in if you want, in 2025. And C, the year in which the population will reach 1 million. Ooh, who knows? I've heard that Wyoming has more antelope than people, and I hope that is true, in which the population will reach, sound this out, Sarah, 1 million. I love Wyoming. All right. Okay, so here's what we know. So let's look at part A. So part A, when you are not given the growth rate right away, right? So I'm gonna look at, this is my population growth function. And what do I know here? I know a couple of things. I know that P naught, or P sub 0, is going to be the first year that I'm given information. So that 494,300, right? That's going to be my initial population. I'm not saying that's the initial population of Wyoming, you guys. I'm saying that that is the initial population of when I'm going to set time 0. So speaking of time equals 0, t equals 0 is going to correspond to the year 2000. So when if t is 1, I'll be in 2001. So t now is defined to be the number of years after 2000. So how am I going to find k? Well, what I need to know, so let's think about this a little bit. So here I know that p of t, then my population function, is going to be that 494,300 e to the kt, right? And what I need to figure out is I need to figure out what that k is. Well, what other information was I given? I was given that there are 564,460 in 2010. They didn't just give me that because they felt like giving that to me, right? They gave that to me because that's going to help me find my exponential growth constant, or rate, excuse me. So what does that say in 2010? What's that information I know then? I know that P of t then must be, right, 564,460, because I know 10 years after 2000, right, that was the population of Wyoming. Okay, so I'm going to use these two facts together to find my solution. So let me clear this out really quick. So this is A continued. So again, I know P of t, right, is, oh shoot, no, I already forgot. What was it? 494,300. Sorry about that. 494,300 e to the kt, right? And I know that, sorry, P of 10 equals that 460. Okay, so I'm going to take P of 10. So I get 594,300. And then I'm going to plug that 10 in. So I have e to the k times 10, right? Because I know that when t is 10, what is this function going to spit out? The 564,460. So that is why they give us that piece of information that when 10 years after 2010, sorry, I'm trying to multitask. I'm trying to put this into my calculator while I'm talking to my computer. I was going to say talking to you, but there's no one here. They give us that piece of information so I can actually figure this out. So I'm going to first, when I solve this, I'm going to divide by the 494,300. 494, 300. So I get e to the 10k. I can't write k10. That drives me nuts. Now, you could actually figure out what this number is, right? Or you could leave it as is if you want to be kind of like me and be really exact here. Oh, sorry about that. Let me silence that. I just got a text from my sister. Aren't you guys happy you know that? All right, so I have this fraction. And now this is so great because look at what we just learned how to do, you guys. In the last section, we talked about solving exponential equations. So what am I going to do? I'm going to take that e, I'm going to move it across the equals sign. And what does that become? That becomes the natural log of this whole fraction. No, you can't do that, but I can because I'm the teacher. All right, so I have I'm going to take the natural log of this fraction. I'm just going to put that fraction into my calculator, leave it in my calculator, and then just hit the natural log of it. And then what am I going to do? So you get about like 0.1327 ... and then I'm going to divide by 10. So when I divide by 10, well, I could do that. I just move it to the left one. What do we get k to be? 0.013. I'm going to go out to quite a few decimal places, you guys. We're taking e, which is about 3, and we're raising it to these exponents. And so it's worth maybe going out a little further because then our results, remember, we're just going to continue using this. It's compounding, right? So our results are going to be a little bit better. So that's my growth rate. And what does that mean? So if you think of that as a percentage, you know, I grow about 1.13%, right? That's the growth rate of per year. That's because T is in years. That's the growth rate of Wyoming, about 1.13%, assuming again that growth is exponential. Okay, so what do we want to find now? Part B is asking us to estimate the population in 2025. All right, so what do I know? I know my function then, my population function, is that 494, yeah, whatever. It's been kind of a long day. 13273t, right? And they want to know what's the population in 2025. So, you know, put in 25. Remember, what does this function do? That's my students said all the time. Tell me, what do you spit in and what does it spit out? Or what do you put into the function and what is it going to spit out? I'm putting in years and this function spits out population. So when you put this into your calculator, please be very, very careful that you take, if your calculator doesn't automatically give you parentheses when you use that E button, you need to make sure that you put parentheses around it. So I'm going to raise it to the E and then multiply by the 494, 300. And here's what we get. So in 2025, the estimated population is going to be 688,811 and 0.48 of a person. You know, we all know someone who really should be classified as about half of a person, but of course we could always round up if we wanted to make that a little bit more realistic. You know that we're going to have about 688,812 people in Wyoming if this growth continues until 2025. Good, pretty easy. And then the last question for this one was, let's determine the year in which the population will reach 1 million. Okay, so heaven forbid the population of Wyoming ever reach 1 million people. I doubt that'll happen. Maybe, yeah, it'll probably happen eventually. And look at this model is going to tell us when it happens. So what is this asking, right? We're not given a time. So again, remember what this function does. You plug in time, it spits out population. So people, don't you dare put that 1 million in for T, right? That doesn't make sense. Put the 1 million is what my population function is going to spit out. Okay. So now I have this function I want to solve for T. It's going to be very, very similar to how we solved for man, I'm having a hard time multitasking today. It's going to be very, very similar to how we solve for K. So e to the 0.013273. I can't guarantee I'm not making mistakes here. I'm kind of recording this lecture on little sleep. which is always a good way to do mathematics for other people, is to do this on full sleep. I'm going to natural log both sides, or I'm going to take the e and move it over, so I get 0.013273t equals natural log. Of course, you could, do this faster, of this fraction right here. And again, I'm not going to write that. So I take 1 million. Make sure I do that. Divide it by the 494,300,000. Take the natural log of that. Okay, and then I'm going to divide by, so what's my last step? Divide both sides by this guy. Right? Divided by 0. Well, that's not actually my last step. To get t it is, but we have to interpret what t means. So I get 0.13273. If I just would have done my notes beforehand and not made things up as I go. I didn't make up the population of Wyoming, but 53.09, let's say. Okay, so you need to think about your answer. If I asked you what year did the population of Wyoming reach 1 million, or estimate that, and you told me 53, oh, look at that. And you told me 53, I would wonder about that a little bit, because in the year 53, there probably weren't even really people in Wyoming, right? Maybe. But what year would it be? Of course, we're going to take that 2000. Remember, t is the years after, and we'll just add 53. It said in what year will it reach it? So it didn't ask you, it'll reach it in the year 2053. So and of course, we'll write this as a beautiful sentence. The population of Wyoming will reach 1 million, or it is estimated that, right? In the year, and pretty close to the beginning of the year, right? But I know it'll reach it in the year, estimated in the year 2053. Okay, I hope that makes sense. These should be pretty straightforward. Population growth, I think, is, once you work with that function a little bit, I think you'll see it's relatively simple to deal with. So another example of population growth is interest compounded continuously. So how do I want to write this? Well, that's exactly what I said. So another type of thing that grows exponentially is interest as compounded continuously. So remember, we talked about this kind of when we talked about the development of the number e, and we looked at what if we took $1, I think we did that, and we saw how much money we could make out of $1, right? So remember, if I have this, yeah, and if I think about, so remember, this is the amount of money I'm going to make, right? This is my account balance, or accumulated amount, when I invest P dollars at an interest rate of R, compounded N times a year for T years. So if you actually invest $1 at 100% interest, so that would be 1, N times a year for 1 year, as N goes to infinity, right, A is going to go to the number E. And you can plug in a bunch of N's and you can figure out that this goes to E. So interest compounded continuously, that's where we're going to get the same formula. That is why that E comes into play. And we don't, the K, again, in this case now, the P naught, that's going to be your initial investment in the account, right? That's your principal. K is actually going to be your interest rate. And then, of course, T is the time in years, okay? So, quick example, this stuff should be pretty easy. So let's suppose, I'm going to actually just give you one where I give you the interest rate. So let's suppose $15,000 is invested into an account earning, I don't know, 4% interest compounded continuously. Okay, interest compounded continuously. What is the account balance? Balance after 5 years, and how much interest was made? All right, so let's just do that one for right now, and then we'll have a part B. Okay, so my part B, I want to know how long will it take to double. Okay, all right, so suppose we have $15,000 is invested in an account earning 4% interest, compounded continuously. So guys, this is pretty straightforward, I think. I think you'll see that. One second, let me clear that out. So what is our function? Well, it's $15,000, right? E to the 0.04 is my interest rate, and my time is t. You guys also may have seen this like in some other life as the PERT equation. That R is just the same thing as K, and P is your P naught. All right, so $15,000, it's asking how much after 5 years. So again, pretty simple. I'm just going to, well, maybe not simple. I mean, show this equation to somebody. I imagine they won't tell you that, oh yeah, that's quite simple. 0.04 times 5, right? I'm gonna raise that sucker to the E, or I'm gonna raise E to that, and then multiply by $15,000. So, ooh, look at, I'm in the money. This is pretty good. $18,000, $18,321, and let's say 4 cents. Okay, so that's how much is going to be in my account. How much interest was made? Well, you know, we had to pony up that original $15,000, so that is not all interest, unfortunately. The interest made will just be that $18,321.04 minus the $15,000, and that's $3,321.04. Okay, I think that's pretty. I hope that makes sense. These functions can get more complicated if they're much more complicated formulas. If we're, you know, saving money like every month and it's compounded continuously. So, I mean, it's great if you have 15,000, you can just plug into an account and sit and watch grow for 5 years. But, you know, how do we mostly save money? Usually we put it in every month. So these formulas can get a little bit more complicated. B, how long will it take for the account to double? Take for your money to double. For your, I don't think I made this your account. How long will take for the initial deposit to double? Okay, so there are a couple ways that we can do this. Well, there's one way that's the easiest, right? So again, remember what this function does. You plug in time, it spits out how much money you have in your account. So now if I look at my account here, what am I given? I'm not given time. I'm asking you to find time, and then I want to know how long it takes to double. So I'm going to take that $15,000, e to the 0.04t, and I want to know how long will it take for it to double. Well, what's double 15,000? That would be 30,000. So the interesting thing about this, so notice, I'm going to divide that 15,000 on each side. You guys, anytime we have a population growth problem, be it money, be it cell phones, be it people, and it asks you about doubling, and we'll talk about this in a little bit, like what does that mean, doubling time? If I'm talking about when does it double, you're always going to get a 2 right here, right? Because no matter what your initial amount was, if I have smiley face, let's say I invest smiley face, and I want to know when I get 2 smiley faces. I know this is stupid and it doesn't make sense, but every time I divide by that smiley face, look at what's going to happen. I'm always going to get 2. This is actually what we call doubling time. You're welcome to look up the formula for that. I don't like looking up formulas for things because I never remember if that formula is correct or not. So anytime I ask you about doubling time, you can always just think about, well, what if I made an initial investment of 15,000 or 100? Doesn't really matter what your initial investment is, you guys. What if I invested smiley face and I want to know when I get 2 smiley faces? You just have to know that they're always going to cancel, and you're going to always get E equals E to the stuff equals 2. Okay, so I'm going to natural log both sides and divide by the 0.04. So if you look up the formula for doubling time, which you are welcome to memorize if you want to, I I don't like memorizing formulas. You get the natural log of 2 over like k or r or whatever you're dealing with. So I'm going to take 2, take the natural log of it, and then divide by 0.04. So how many years will it take for my investment to double? It looks like t is going to be about 17.33 years. So 17 and, you know, a third. 17.33 years for my initial investment to double. Okay. All right. I think that's pretty straightforward. I hope that makes sense. Again, you can, well, let me just do one more example really quick. Clear. Let's look at, let's just say you have an account. How long will it take for an initial investment to double in an account earning .5% interest compounded continuously? So I just want to, I know I might be beating a dead horse here. I don't actually do that, so you guys don't have to freak out. Okay, so I just want to point out, I want to do this quick example because again, you can go ahead and you can memorize some formulas, right? Or we can just kind of think about it a little bit. I know, again, asking a lot. So what do I know here? I know P of T, right, equals P. I don't know what my initial investment is, e to the 0.035 t. But what I do know is I do know that I want the time it takes for my initial investment to double. So remember, this is my initial investment. So my initial investment being doubled, what is that? That's just 2 P naught. I'm going to divide by P naughts. Those cancel. I'm going to take the natural log of both sides. So I'm going to get e to the 0.035 t. Oh, no, I'm sorry. I said to take the natural log, didn't I? I'm not even listening to myself. Man. So I get 0.035 t equals the natural log of 2, and then divide by that 0.035. Okay, so natural log of 2 divided by the 0.035. So what is my doubling time for this account? My doubling time for this account is 19.8 years. Okay, again, don't have to memorize a formula to do that. We can also do that with K. Like if we wanted to know, you know, if I wanted to double, let's say I wanted to double my investment in 10 years and I wanted to know what percentage rate would I need to do that, you could solve this exact same way and solve for K just like that as well. All right, guys, we're at a half hour. I think I'll stop this right now. That was population growth. What we're going to look at next is we're going to look at, well, what if we have a population that is limited somehow? Okay, so it's still maybe an E is involved and it's still a growth, but it's not going to grow exponentially necessarily like we have before, in the sense of what everyone thinks it is. And then we're going to talk about decay. So that'll be part 2 of this thrilling series of exponential models and applications.